This is a DigiConnect ME, a standalone network communications device. It is designed to be integrated into embedded systems that need a network interface. In appearance, it looks like a simple Ethernet jack. In actuality, it is a fully capable, general-purpose computer. In addition to supporting network communications, the Connect ME can run any desired application that fits within the limits of available processing and memory resources. The Connect ME and related Digi products are used to provide networking capabilities to embedded systems in a wide range of industries, including utilities, transportation, facilities security, healthcare, manufacturing, and many, many others. The Connect ME includes a software stack supporting the TCP/IP network protocol stack. As we can see, the software stack supports a complex, layered set of communication protocols. While the protocols themselves are for the most part secure, vendor implementations of these protocols frequently are not. Past testing has found implementation errors in vendor software supporting many of these layers, for example, IP, TCP, TLS, and HTTPS. These errors introduce vulnerabilities, which can then be exploited with effects including leaking confidential information or even fully privileged remote code execution. Remember, the Connect ME is a fully capable computer. This means that a successful attacker can load and run programs directly on it. On Adventium Labs' VOLTA project, part of AFRL's NOVA program, we have developed an analysis process for testing networked embedded systems by learning their input-output behavior, including the timing of that behavior. VOLTA supports this analysis by identifying and investigating the implementation of both known and unknown protocols. In previous work, we have demonstrated the utility of VOLTA's timed automaton model, identifying timing-related flaws in a digital door lock system, detecting vulnerabilities in a fielded off-grid communications device called the GoTenna, and discovering an exploitable weakness in a safe with a digital lock. Building on these successes, we applied VOLTA to testing the TCP/IP software implementation on the DigiConnect ME, which uses TCP/IP software from a third-party vendor called Treck, which has been shown to have multiple vulnerabilities. The vulnerable Treck software has been used in a host of other devices. In consequence, these vulnerabilities can be found in a wide range of industrial and government applications. The question we set out to answer: what other problems can we find related to one or more of these vulnerabilities? To answer that question, we decided to explore a subset of the protocol stack which is known to contain several vulnerabilities. We chose IP over IP tunneling, which is frequently used for virtual private networks and other means of safely passing messages from one secure network to another. Fully exploring even this subset of the protocol stack requires tests involving hundreds of thousands of distinct messages. Using VOLTA's alphabet abstraction process, we grouped them into a much smaller set of message classes covering the same area, but reducing the number of test messages to 450. With those 450 messages, we used VOLTA to test the Connect ME in this newly defined search space, generating a learned model of its behavior. This simplified version of the resulting model depicts a summary of the behavior of all the possible message sequences that VOLTA learned. The model from which these results were derived took about 30 minutes for VOLTA to learn, as opposed to the hours of fuzzing or days of manual investigation that would otherwise be required. Here's what VOLTA uncovered. First, VOLTA confirmed the existence of a known vulnerability. Identified by the JSOF Research Lab in June 2020, this vulnerability can be exploited to leak sensitive data. More significantly, the learned model also revealed that the originally published exploit for this vulnerability can be triggered by a wider range of messages than previously reported. Investigating a different part of VOLTA's learned model revealed a more effective exploit for the same vulnerability, which can be triggered by a different and much larger set of messages. This exploit has the potential to leak 10 times as much data as the original exploit. Finally, VOLTA's learned model exposed some additional anomalies, the full implications of which we are still studying. In one of the anomalies we found, the ConnectME is accepting and processing invalid packets even though it recognizes them as invalid and generates an error message. In a second anomaly, the ConnectME is incorrectly generating an error message for valid packets. Despite classifying them as invalid, it is still accepting and processing them anyway. We have now shown that VOLTA will be of practical use in finding and delimiting errors in various protocol implementations, including within the TCP/IP protocol stack. Communication interfaces for these embedded systems are increasingly reliant on these complex, multi-layer protocols. Combined with our previous work, we have demonstrated the utility of VOLTA's timed automaton model for use in testing and analyzing input-output behavior for a wide range of networked embedded systems. Based on this success, our future work will focus on maturing and extending VOLTA for transfer to government and industry technology partners. For more information, go to www.adventiumlabs.com.